Hello everybody, nothing like making a nice little video here after our ACT tests are done. So this is our official presentation of the law of cosines. It is section 2.5. I'll be attaching notes that match with this. You do have older notes, and the two samples today at the end do match those notes we already have downloaded. So here we go. Just as a reminder, this law of cosines is related to the Pythagorean theorem. So we all know that the Pythagorean theorem works in right triangles only. If we want to try to use something like the Pythagorean theorem for any triangle, we need to have more to it. We need to add something to it. We need like more power, shall we say, which is where our next slide comes in. We've already even used the Pythagorean theorem. If it doesn't work and it's not exactly equal, we can tell if a triangle is acute. Basically, if our c squared is too small for what it should be for a right triangle, we know that the triangle then must be acute, right? This side here would have kind of had to squeeze down and leave only the length that we have for C. So to make the Pythagorean theorem work here, we need to use something a little bit different. We need to add something to it. And this extra fudge factor, we got things mushed together here. This extra fudge factor is what we need. It is called the law of cosines, and this is what I mean by that extra fudge factor. Let me find a new color here for my highlighter if I can. It is this piece right here. This is the part that actually makes this a squared plus b squared big enough or small enough that it matches the c squared. And notice, since it's called the law of cosines, it makes pretty good sense we'd expect to see a cosine in there somewhere. Okay, so that's basically the law of cosines. It's very, very, very much like the Pythagorean theorem, and it does work now not just for right triangles, but for any triangle. And actually, it works for any side of the triangle. So notice here we could solve for a squared, and of course the last step, once we get numbers in place here, 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 and here, where I underlined, we're going to have to, of course, square root that because it does say a squared over here. Right? For b squared, right here, same thing is true. If we have numbers for a and c, they go here also, and an angle cos of b, we do have to actually at the end square root because this represents b squared. So we can essentially solve for any of these letters, a or b or c, if we know the other information that we need. So we simply plug in numbers and crank away. Notice that each of these versions has symmetry, so they're easier to remember. It just turns out that way. So notice they all start a squared plus b, a squared equals b squared plus c squared. Very similar. Also note that this first letter you're solving for matches at the very end your angle letter. So this side you're solving for, a squared, is the side directly across the triangle from this a. And the same thing happens if you notice for b squared and angle b. Solving for c squared, you need to know angle c, for example. Also the other pieces involved. If there is an a here and a c here, the AC are right next to each other after the 2. If there's a b squared and a c squared, there's also a b times c in the first version, immediately following the 2. And in the last one, you see the same thing happening. So once you write these a few times, they pretty much just almost write themselves after a while. Okay, so to find a missing angle, which we can use this for also, we have to get this cos of a expression by itself. And then, of course, once we do that, we would have to use inverse cos of the answer that we get to find the angle measure. That should be kind of familiar. So our job is to get cos of a by itself. So how in the world do we do that? Well, I think we know. We first start to subtract things away from the cos of a, and the first steps would be these to get those away. So we'd have a squared, let's get rid of that. That should be a plus, right? Okay. a squared minus b squared minus c squared equals negative 2bc cos of a. So we're starting to pull it away. Also, something else we do want to kind of take care of is this negative sign. And to do that, we can multiply by, let's erase that guy. Change back to my pen. Multiply by -1 both sides, and the effect that will have is to change the signs on everything we have, like so, and I just happened to write the ones I knew would be positive first. And when I do that, I have now just 2bc times the cos of a. We're almost home. Last step here, I need to get rid of the 2bc by division. So over here I'm going to have 2bc, and these happen to cancel out. And then I have cos of a by itself. Now it's a little bit tedious to do this all the time. You need to look for an angle. But notice on the other side now we have something that we can actually kind of make use of. And there is some symmetry over here as well. Notice this last guy that's all by himself, the little side that's squared, matches the cosine of the angle we're looking for. And at the same time, over on the other side, the parts that are added together, the b squared plus c squared, also show up in the bottom. So that can be a handy way to try to remember this next version. So if we're solving for the cos of, got that done. There are a couple of versions of this, and these are all three versions together on one page, a little bit smushed together. But if we are solving for an angle, for example, angle A up top here, that means we would need to know the values for the B, the C, and the A. In other words, we're going to have to know all three sides to be able to solve for an angle. With that, we'll end our discussion of what the law of sines is and actually use it in the next video.